So you can see the slides now?
Yes.
Oh, yes.
Cool. So we are Julian, Leonard, and Mariana. And I just realized that Julian's name is wrong. So I'm going to correct that super quickly. I'm so sorry. Okay. Now we can start. We did a NFT similarity search engine. So what are the NFTs? So it's called non-fungible token. So it's a piece of data that is virtual, so it's on the internet, and it has an owner, and the ownership is recorded in a blockchain, and it's used for trading, so people can sell their NFTs or just keep them, and then the value will increase and so on. And because it cannot be subdivided, so it's like other assets, like the currency, you can always break it in little pieces, but with these ones you only own the picture or the game or a song, or can be any kind of artwork, games. So they stay as a single whole thing. And so there are usually, there are ways to classify them. And usually it's done with supervised learning, so using labels, for example, taking into account the collection of their work. So we're talking about images from now on. But we wanted to build something that didn't depend on labels, but that actually looks at the intrinsic feature of the image. So then we tried to do some unsupervised classification. And the idea was to produce a software that will provide the user suggestions of an NFT artwork that they would like to get. So the problem is that usually with suggestions of images, the engines right now are not so good. So you can put a picture online, but the suggestions that are given are not so good. So then we wanted to try to find a solution for this. So the aim is to make a similarity search engine that will provide NFT recommendations based on visual features of the unlabeled images. So first we collected the datasets. We collected a few collections, but we based our project on two main ones. One is the Solana collection and one is Bored Apes collection. So Solana is a group of smaller collections. So we got 100 collections of 100 pictures each. And then with apes, we just got 1,000 pictures. So it's the same size. And then we divided them in train and test. But at the beginning, we weren't so sure of how we will approach the project. So we tried to follow the traditional approach and have a train set and test set. Then we had to resize the images to 128 by 128 pixels, so it's easier to handle them. We tried several things. So originally we wanted to use ImageNet. So ImageNet is a supervised trading model that is used to classify images. So there is an online database called ImageNet that is a huge database of pictures that is used for training machine learning models. And there's a competition where people go and test their model to see who achieves the lowest error. So then ImageNet has, I think, 20,000 classifications. And then there are all the images. Well, there are millions of images that the users upload into the database. And then, so it's a lot of data that can be used for training any model. So then there's this collection, there's the competition to see who classifies the pictures the best. And ImageNet was a winner, and I don't remember the year, but it's a really good model. But then we realized that it's supervised training, and we wanted to try something different. So then we tried to use k-means clustering, which basically looks at all the features of the pictures without giving it any metadata about the image. And I tried to group them in different classes, but it didn't really work out, so we were just getting like a class for every image, and yeah. So then we tried another approach, which was the Euclidean Distance, pixel-to-pixel comparison. And Lena will explain more about this. but basically looks into the colors of the image. It compares the image depending on the color. And so we got finally some results, but then we wanted to have a classification that wasn't only based on the color, but actually that look at other features of the images. So then we try the VGG16 it's a convolutional neural network. And so we passed the images through this network first, and then we took the output vector from the network, and we compared this using the Euclidean distance. So then we had another, we had the comparison based on the output from the neural network rather than only the color. So Julian will explain a bit more about this. And finally, we try again a clustering with k-nearest neighbor, just to test and see if we can have a better result with the VGG output to cluster the images. And yeah, then we just compare the different methods that we use. Cool.
Should I jump on the data collection? Yeah.
Mm-hmm.
So we found some data sets on Kaggle, the famous data analysis community, and so there were already some data sets for both the Bored Apes Yacht Club and the Solana NFT collections. But then we needed some. Can you show the next slide, please? We needed some complementary data, so we've been using the OpenSea API. OpenSea is the most popular NFT marketplace, and we've also been using Selenium to take screenshots of the images based on the URL that the OpenSea API provided us. So that was a way to collect the images because the image dataset were not available to download directly. And then we've been encoding the images with base 64 encoding, so that then we had a dataset, complete datasets with the name of the collection and the images that was encrypted as a string that could be recovered with some dataset loader. Next slide, I guess.
Yes, thank you so far. I'd like to explain now the baseline model that we tried for the pixel comparison, meaning only getting our thing for the colors. Next. This is it the first? No. Wasn't there one before?
Can you go back, Mariana?
Yeah, go back.
Actually, I can't. Just maybe one of you wants to share instead?
I could try, yeah.
Sorry.
No problem. Yeah, so yeah, shown before. First, we just did some typical stuff like importing the images, as Julian showed that we got the images and had to encode them via base 64. This works in a way I will explain next. But first, we just got the certain images from either dataset, either it was the Apes collection or the Solana collection, and we had to resize them and then put them into a new vector so we can later work with them. So the base 64 transformation works in a way that we just get a, I would say, collection of numbers and letters. For me, it does not make sense really, but the computer can work with it. So from this, we can encode it, and we get a vector of the size of the pixel size from the picture times the RGB value, which is 3. So typically the pictures were 500 times 500, and we then flattened it or resized it to 128 to 128 times 3. And this in the end looks like something like this. After we resized it, we flattened it, so we only got one vector with the size of, I think it was about 500,000 to 1, so 50,000 values that we got. And after this, we created a new dataset which contains all the images, meaning every column represents one image, and considering the amount of the images we took for one try, either it was, let's say, 5 or the whole dataset, meaning 10,000 pictures, the dataset would be that long, and every column represents one picture. After this, we get to the comparison, which we did via the Euclidean distance. I would explain, maybe you can see it also in the code, but in the end, we just take the first pixel of a picture and compare it to the first pixel of the second pixel. Then we get a certain distance, and after this, we do it for every picture, for every pixel of the picture, and then together this will align to a value which we can work with. So first we wrote the function. This is the first thing you can see, the Euclidean distance, and after this we created an array which we'll use to compare it to, and then we just run it through every picture, meaning the given test image which we imported will be compared to every picture in the dataset, or more, every vector by now. So this is the function, to keep it short, but the first value will be the second value. First value of the first picture will be subtracted by the first value of the second picture, and this will be squared, and these all added up gives us a value, and these values in the end will be saved in a new array. So let's say we got 50 pictures, we ran this through, meaning we got 50 values, and this gave us 50 values, and 1 was the lowest, meaning out of these 50 values we got one value that was most near to the given test image. And if we now go further and try to run it, let's say I think we first tried only on 10 or 50 pictures, but we ran it on all, we got results like this. So on the left we can see an ape that we tried to test on the Solana dataset, and first it looks like really similar, but this is due to the colors. So I think if you would take a larger look and don't really can see the pixel details that we took in, but only the colors, it would work quite well. But the thing is, we didn't want to recommend the user just look, you like yellow pictures, here's a yellow picture also. And yeah, due to this, we get a certain bias, meaning that, let's see on the right, it takes the same collection, but the thing is, it's most based just on the background, and this was a little bias which we had to fight with. If we look on the next slide, here's an ape we tried on the ape dataset, and it looks quite well. I mean, if I would see the picture, the bigger picture on the left, it would work quite good because the recommendation seems very similar. But the problem is, there's, I don't know, you can say, oh, he smokes a cigarette, so everybody else smokes a cigarette. Later we refer to this, but we just saw the background, and this also happened for the Solana. We only tried Solana, and also we couldn't figure out how the model came to the conclusion that the orange picture on the right top fits into this. I mean, the other 3 pictures are dark, so this fits quite well. I mean, the distance won't be that far, but orange and dark blue is, so this, we couldn't learn much out of this. After this, we tried the first picture again on the collection of both datasets at the same time, and now we got either weirder results. If I go back to only apes, we can see that the background at least matches, but here it's not all the same, so this was a bit confusing. Yeah, and after this, we tried to implement a new model, which will brought to you by Julian now.
All right. Yeah, thank you. So yeah, we were not satisfied or a bit confused, we'll say, by the pixel-to-pixel comparison, and so we used the CNN called VGG16. It is pre-trained on the huge ImageNet. It is composed of 13 CNN layers, 5 max pooling, which has the effect of emphasizing small areas like shape related areas in an image. It also had 3 ReLU activation and 1 softmax at the end, because what the VGG16 model is doing, it's taking an image of a certain size crossed by three let's say layers of colors, and then it converts it step by step in a large vector with features. And can you show the next slide? Thank you. So then what we did is we are processing each images with VGG16. So the code looks like that. We are looping in our dataset. We are decoding first the base 64 image. Then we are changing this image in an array. We are reshaping it, resizing it, and we pass it through the VGG, which then gives us a vector that we reshape, and this is saved as an output, the output of the VGG16. And so each image passed through VGG16 is saved in a new dataset that we call the VGG dataset. Next slide, please. Yeah. So then we are again using this VGG16 output to compare the Euclidean distance between images. The vectors are quite different actually when you look at both vectors, the pixel to pixel and the VGG16 output. The pixel to pixel tends to have a lot of numbers, like all pixels have an activation, and so it has lots of numbers. Versus the VGG16 vector, that is a lot of 0 actually. So we can really see that the model is now focusing, the vector is now focusing on the visual features that make sense in the image. So we reuse the Euclidean distance to compare images like that. Next slide, please. And yes, this is the piece of code. So to visualize the closest image, we are calculating the minimum distance. So we take the test image and we calculate the distance between the test image and each image in the dataset, and then we retrieve the image that is the closest, so with the lowest Euclidean distance in the whole dataset. Next slide, please. And that's the result actually. So we can see now that probably the model focuses less on the background, which is a good news. That's what we wanted to achieve. Then with human eyes, it's always a bit hard to evaluate the performance, right? We can see that, okay, most apes have the same skin color. The background is similar but not necessarily the same. They tend to be a bit minimalist as well in terms of features. They only have one hat or mostly that's it, hat and sunglasses. Next slide, please. We did the same with Solana. Here is quite interesting. If you remember what we've seen with the pixel to pixel, it was much more random actually. Now we can see that, okay, we have the same animal on most images. Then there is a shotgun. I don't know why, but anyway, most images are providing the images that make sense actually compared to the test image. Next slide, please. Okay, and then we cross again the apes and the Solana datasets, and here, well, we have something that's quite hard to evaluate. To be honest, we can talk about the pastel color in the background, but still, yeah, not sure what to say about that. Yeah, that was the result. Next slide. Yeah, so then we've been trying to use KNN clustering on the unlabeled images by using the VGG16 output, which seemed to us more obvious than the pixel one. And what we can see here, so the idea is, since there is 100 natural collections in the Solana dataset, we decided to check what's the best number of clusters between 1 and 100 for both datasets. So we had something to compare. And actually it's quite surprising. So okay, for the apes, it might be a challenge for the model to tell him, okay, you have 10,000 images and give us the best number of clusters. And so the first slope that we had was very smooth. So it's like, yeah, it makes sense. All images are very similar. They are all in the same collection. So it makes sense that, yeah, there is a smooth slope going from 1K to the other, one number of cluster to the other. But that was more surprising for the Solana collection. I was really expecting that the model would recognize, since there are 100 natural collections, it will say, okay, yes, K, the 100 clusters is a good fit for clustering without labels the Solana dataset. It appears that not. The slope is a bit more noisy than on the apes, but still we cannot identify ideal number of clusters for this dataset. So I'm not sure the KNN clustering is working very well, to be honest, on the VGG16. And yeah, that's what I had to tell you. I will give the hand back to Mariana.
See to the previous slide, please. So just one comment. If you see there's a difference in the initial squares in apes, it's lower than in Solana. So it could be because, and also like the final one with 100 clusters is also lower. So it's showing us that the apes is the same collection, so they are all like 8 pictures, so very similar, and in Solana we have more diversity. So next one. Well, here we compare using VGG16 and not using it, only with the Euclidean distance. So we can see if we don't use it, we got 2 guys. So the one on the left is the one that we want to compare, and then the ones on the right are the option that we actually get. So the lower one, we get an option that he has hair, like curly hair, and this Greek plant on the sides, but the skin color is similar. So I think this is why we got this result. And then the upper one, the skin color is totally different. However, the shape of the head is like round, so it's more similar to the one that we want to compare. And also he has a t-shirt. So you can see how the 2 models look at different features of the images. And so we have to remember that the VGG16, it actually compares the final vector that it gives us is comparing the pictures with the classes in the ImageNet dataset. So it has been trained with a lot of different images. So of course, if we had trained it only with the pictures in Solana, for example, like in one single database, then we can start saying like, okay, this one means t-shirt, this one means a band on the head, this one means a heart on the skin, so it would be way more accurate. But at least here, I think that it's recognizing some of the features. And of course, if we wanted to train on our datasets, then we need to label the datasets, and that's kind of what we wanted to avoid. So it's kind of a circle there. So next one. And yeah, so this is with Solana. And without the VGG16, it's definitely much worse. So to a human eye, this has nothing to do with the sample image. But of course, for the Euclidean distance, well, it's a black, dark background with something bright in the middle, so then it makes sense that we got this answer. While with the VGG16, we definitely got the same shape, even though the colors are different. And he even has like a hat and something on the accents. With Solana, it worked really well. So next one. With apes, I think it has to do with the fact that the ape images are already very similar between each other. So to humans, and at this point, we actually focus more on the colors. Because if I see those apes, well, first thing I see is the background. Then, okay, the skin, one is white and the other one is pink. But then so that's the four, but the actual skin is the same color everywhere. So. And then we also got the same hat. So the Euclidean distance is not so bad for comparing apes because they already have the same shape. So really the thing to discriminate would be the colors in this case. And then with the VGG16, sorry, let's see. Having a noisy street. So with the VGG16, originally it might seem worse, but if you look at this part, the beard, he actually has beard. So I think that's what the VGG16 is using to pick this picture instead of the other one, because this one is totally in shape. Yeah, next one. And then this is comparing the one picture from A, again, some Solana pictures, but there I wouldn't. I mean, it's good. We know that this one down on the bottom right is an ape. So, but I think it was more like a lucky shot. And the one on top, I see that it has like the shape of the mouth and then the eyes. So I think that's what is looking for the comparison. But it doesn't really work so much if we try to do a cross comparison, combining two different collections. Next one. So just to conclude, using only Euclidean distance is biased by the background color. And then the VGG16 focuses more on the shapes and the things that are actually in the picture. So it improves the results in the Solana collection. And the apes collection, most of the pictures are similar, so both methods work okay, I will say. But yeah, for Solana apes comparison, we will need to a bit more work. And that's it. Thank you very much for listening.
Thank you.
Thanks a lot. Very nice presentation. I enjoyed.